All right, hello. This time we are going to go through the makeup work because I have a conference to go to, Hakwe. So if you see the website, you can see on the left some new slides. There's not an image here yet, but I'm going to update that so that you can see the image properly. And then you can click on the slides. The first slides, today's chapter is going to be about measurement, reliability, and safety systems, which is kind of interesting. Some of the contents in here are going to apply later when we do some more sensor monitoring with our Internet of Things device. And then slides 2, we'll install MQTT server, the mosquito server, so that we can get that running, go through some of the setup on that, and then we're going to run through our Internet of Things device a little bit. So let's just take a look at the LMS makeup slides really quick. This is understanding device analysis from a software, digital perspective kind of thing. Anyway, chapter 12, measurement, reliability, and safety systems. In here, we'll talk about reliability first, safety systems second, and then there's a nice summary. There's a lot of subsections, so let's take it slow or fast, not sure yet. This chapter explains how measurement systems fail, how reliability is measured, and how reliability can be improved, and how safety systems are designed to prevent dangerous industrial situations. Actually, this is really important these days. One of the things that we can do now for preventing dangerous industrial situations, or what they're working on right now, is using CCTV cameras to identify workers in the industrial work environment. And when they get too close to a machine or something like that, there will be a kind of a warning, or it can shut down a machine that's too close to a person, or there's various different things we can use with cameras and smart devices and AI systems and things like that now. So I mean, that's kind of nice. That'll be good in the future. All right. Continuing on, it also explains why software reliability is different from hardware reliability and introduces industrial safety standards such as IEC 61508. Let's check the IEC 61508 really quick. Maybe we can link to it. IEC 61508 is the foundational international standard for the functional safety of electrical, electronic, and programmable electronic systems. It mandates a comprehensive life cycle approach to design, build, and maintain automated protection systems to ensure they fail safely or function perfectly during emergencies. That's important. You have to fail safely or function perfectly. If you just shut down something improperly, it could break, it could cut off somebody's arm, something like that. So fail safely. If it's going to fail, make sure it's a safe fail, or function perfectly even during emergencies. Very nice. These are some of the concepts that we're going to talk about today in this slide. Safety integrity level, safety life cycle, systematic and hardware safety, and industrial applications. There's other ones down here that are very important, but anyway, that's a breakdown of the core concepts. Here's an overview. I'm going to link that. I mean, you can search it yourself later, but I'm going to link it anyway. Just for fun. I have 2 slides open, looks like. Okay. Let's link it. Okay. Next, introduction. Measurement systems do not remain perfect forever, obviously. That's why we have to recalibrate things. Over time, things age, sensors drift. We have to recalibrate things. Faults develop, measurements become inaccurate. Complete system failures even may occur. So in safety critical environments such as big industrial plants, things like that, these failures damage equipment or kill people. Interrupt production, put human lives at risk, create dangerous conditions. There's this one crazy video I saw of something like this that happened. This one. Portal to hell in an aluminum plant opens. This one was crazy. Let's take a look at this one. This one was really, really crazy. This is what happens when things don't go according to plan. They don't end up safely. This is super crazy. I'm going to leave it in here, but then we can watch it over here on this. It's an aluminum factory, and then something starts happening up there, and it just starts spouting, whatever it is, chemicals that turns into fire, and then literally within seconds, the whole plant is gone. Yeah, like there's the roof melting, and it's gone. It's basically gone. Look at that. The whole thing just caught on fire. It's so flammable. Wow. Nuts, right? That's why it's called a portal to hell. Opened at an aluminum plant just from one small thing. That whole thing is gone. Jeez, that's nuts, eh? Okay. Yeah, great. Okay. So this chapter studies reliability theory, reliability calculation, hardware and software reliability safety system design. Reliability means how dependably a measurement system performs its intended function over time. If it has problems, faults, for example, it may result in incorrect measures, missing outputs, unexpected system behavior. So reliability is statistical. We can measure it statistically because manufacturing tolerances vary. We can measure the tolerances, operating conditions differ, and random failures occur. So there are some statistical ways we can measure reliability. It's formally defined as the ability of a system to perform its required function under specified conditions for a specified time, and these are some of the ways to calculate that. The first way is mean time between failures, called MTBF. It measures the average operating time between failures. So we have this formula here, which is the total operating time and then the total number of failures. So for example, if failures occur in this pattern, there are 18 total failures here, I believe. So after every, so this is kind of randomized, right? It's like if you work in a power plant and somebody has an accident, it's like those signs that they used to put up, how many days since an accident. Especially this was really common in Simpsons. X days since last accident. Meme. Okay, let's look at some memes. This will be fun. 0 days since last accident. See, it's in like Simpsons and all kinds of different places like that. 0 days without accident. 0 days since last acquisition. 0 days without accident. Kind of like that. I should shut that down. 0 days since last accident. Yeah. That's an even better one. There. That's kind of what it's supposed to look like. He's taking down the 32 and he's putting up 0. And that's how a lot of plants, my dad used to work at a plant, that's how a lot of plants record stuff, and my dad's plant really recorded stuff like that. So let's say after 11 days there's a failure, then after 23 days there's another failure, after 27 days, after 16, 19, 32. Well, but in 360 days, in almost a year, how many failures occurred? 18. So we take 360 days divided by 18, and that makes the average, the mean time between failures is 20 days. You can see some of them are low, like 12, 11. Some of them are high, like 32, but the average is 20 days. That's MTBF. The next one is mean time to failure. So this is used for components that are discarded after failure rather than repaired. Yeah, so for example, we're expecting something to fail within a certain amount of time, so after a certain amount of time, we just throw it away. Examples are thermocouples, light bulbs, disposable sensors. Suppose a batch of 20 thermocouples is put through an accelerated use test in the same environment, and the simulated time before failure in months of each device looks like this. The mean of these 20 numbers is 10, therefore the simulated MTTF is 10 months. Even though some of them fail sooner and some of them fail later, the average MTTF, mean time to failure, is 10 in this use case, in this situation. The third principle of reliability is mean time to repair, which measures the average repair time after failure. We would have a lower MTTR. It improves the overall system availability. Yeah, the faster you can repair it, the more available the system is, right? So for example, right here, as an example, suppose the time in hours taken to repair an instrument over a history of 18 breakdowns is recorded with the following times measured. The first time your internet breaks, it takes the repair guy 4 hours to get there. The second time, he gets there in only an hour. The third time, it takes him 3 hours. The fourth time, it takes him 2 hours. The fifth time, an hour. The sixth time, wow, he's in another city. It takes him 9 hours to get there. Something like that. You average all of these up, and then it becomes 3. Therefore, the mean time to repair in this situation is 3 hours. You can expect when you give a phone call to the mechanic or the repair guy, it's going to take an average of 3 hours for him to show up and repair your stuff. Okay. And then we can talk about availability. So availability is kind of a sum of all of these things. Availability measures how often a system is operational. So we have the mean time between failures divided by the mean time between failures plus the mean time to repair. Yeah, and that's how often it's available. It's not available when it's broken. So this is how often it's going to be available, basically. Good systems try to increase mean time between failures. Yeah, longer periods without breakage is very good. And decrease mean time to repair. Faster the mechanic gets there, the better. Here's an example. Data are collected by a manufacturer about a particular measuring instrument that is used 24 hours a day, 7 days per week, recording both the interval in days between breakdowns and the time in days to repair each fault that causes a breakdown. Here are the data. Time before breakdowns, this is MTBF, right? Time to repair faults, this is MTTR. And then calculating these things, MTBF would be 14.5 days between failures, and the mean time to repair is going to be 0.92 hours or something like that. And so the availability of this particular instrument is 94%. So about 6% of the time you can't use it, but 94% of the time you can. Now, the worst situation would be if something is 70% available. Like 30% of the time you can't use it. That's not dependable at all. Okay. Or not reliable at all. That's the key word, I guess. Okay. Principles of reliability include failure patterns, such as the bathtub curve in electronic components. There are 3 regions that exist in this bathtub curve. Early failures on the left, stable usage life in the center, and then wear out failures at the end. This is over time like that. The last one down here is for mechanical components. Mechanical components don't usually have early failures like that. So manufacturers often perform burn-in testing to eliminate weak components before shipment. Yeah, that's true. They do that with semiconductors too. They test semiconductors before sending them out so that all of the bad chips that are going to have failures at the beginning, they just get rid of those before they put them on the market. So then you can produce this kind of curve. You reduce the early failures or effectively eliminate the early failures. So everybody who buys your product is pretty much happy with it. This is a really good way to sell products, not 100% of the products that come off the production line are going to be stable. So you get rid of the unstable components first and then just only sell the good components. So then everybody's happy. You can get high reviews. Mechanical components usually fail because of fatigue, friction, wear, and aging. And so, yeah, this is the curve for mechanical components like that. They don't usually have as much early failure. So failure rates increase over time, obviously. Principles of reliability are, in probabilistic terms, reliability can be expressed in this way. FT is the probability the system fails. It would be 1 minus the probability the system survives. So over time, the probability of the system surviving is lowered. So the failure probability is higher, right? Raised. And this is the equation of how they calculated all of that, how you can get to that. As the limit delta t approaches 0, the instantaneous failure rate at time t is given by that final equation. So this is how all of that is kind of worked out using n number of identical instruments, etc., etc. You can read that yourself later if you are curious. I provided it for your reference if you are curious. Exponential reliability equation also exists here. For constant failure rate systems, the reliability is equal to the exponent of minus. This should actually be theta. Over here you can see it's theta f. I copy pasted wrong. Theta f instead of qf, so theta f t times t, the time, where theta f actually is the failure rate. and T is the operating time. The reliability decreases exponentially with time. So, like maybe after the first failure, it's not that bad, but after, 2, 3, 4 failures, you better get rid of that quick because it's just going to die. Actually, I had a keyboard recently right here. I had a keyboard kind of like this one that I used it for 6 years or something like that. I don't even remember how long I used it for. And then within the last month, it failed twice. After I changed with completely new batteries, it failed twice, and I was like, that's it, this thing's dead. So bye-bye keyboard. That sucks. Here's an example. If the MTTF, the mean time to failure of an instrument, is 50,000 hours, calculate the probability it will not fail during the first 10,000 hours of operation. So in this case, what is the probability of that? The exponent of minus 10,000 over 50,000 is 0.8187. That's a pretty good non-failure rate in the first 12 or 10,000 hours. That's 82% not going to fail in the first 10,000 hours. If the MTTF of an instrument is 80,000 hours, calculate the probability it will not fail during the first 8,000. So in this case, 80,000 divided by 8,000 is 0.1. So we can apply a different equation, giving this 1 minus t equals 0.9. It's 90% accurate, or 90% non-failure rate. There's a very small level of inaccuracy involved with that expression, however. If you calculate the probability according to the exponent right there, then it actually comes out to 0.905. So it's a really small but finite error depending on which equation you use. So this one is good for simple equations. It's good for estimating, but it's not completely accurate. This one is more accurate for that kind of thing. Okay. Laws of reliability in complex systems. Measurement systems contain many connected components. Overall reliability depends on how components are arranged. We could arrange them in series, in which case failures of one component cause the total system failure. That's like old style Christmas lights. You may not have ever seen old style Christmas lights, but it's like you have these lights just strung up on a string, and if one of them fails, like the whole string is dead. So then what my dad used to do if we had a string of lights that failed is my dad used to sit there and go through each light, testing each light to see which one was the bad one. He would replace and, put in a new light, each one, to try and find out which one was the failure. Like leave it plugged into the wall, because you could kind of be safe doing that. Well, the very first ones, you had to unplug, then switch the light, then plug in, test it, and go down the string like that. But after a while, you could just leave it plugged in. Anyway, if a measurement system consists of a sensor, an output conversion element, and a signal processing circuit, for which the reliability figures are 0.9, 0.95, and 0.99, calculate the reliability of the whole measurement system. You just multiply all of those together because they're in series. It's a series, right? Multiply together. The reliability of the whole system is 0.85, because you never know when any of those are going to break. So here is the reliability of components in parallel. They improve reliability because the system fails only if all the components fail. Parallel redundancy greatly increases reliability. This is an important keyword, redundancy. Yeah. So here, Fs is the unreliability of the system. And then it's similar right here for n instruments. And Fx is the unreliability of each instrument. Because they're all in parallel, you could just take the unreliability of each instrument, like 0.9 to the n power, to the third power, like the previous example. So in a particular safety critical measurement system, 3 identical instruments are connected in parallel. The reliability of each is 0.95. What's the reliability measurement? It's 0.95. Actually, to find Fx, we have to take 1 minus Rx, the reliability. So the failure percentage is 0.05. That's the one that you cube right here. So the overall failure of the system would be 0.000125, and then the reliability of that system would be 0.99, so 99.9% reliable in a parallel system, compared to 85% reliable in the previous system. Much better. Improving measurement system reliability. Some ways to do this are choosing better instruments, protecting your instruments better with things like insulation, regular calibration, keeping them up to date with calibration, redundancy, very, very important keyword. The whole internet is redundant. Early replacement before wear out failure region. Yeah, so when we calculate the MTTF or whatever, mean time to failure. No, mean time to, what was the second one? Yeah, mean time to failure, I think. Yeah, mean time to failure, that's when it's going to be dead. MTTF, Majo. So MTTF, when you calculate the MTTF, you could replace things before the MTTF to reduce the wear out failure region. Yeah, or before it gets there. Choice of instrument. Here, reliability depends strongly on operating environment, such as temperature, vibration, corrosion, humidity, and dust, like that explosion in the aluminum factory we just watched. Those are environmental factors sometimes. Okay. Instrument protection. Sensors must be protected against harsh environments. We could use thermocouple sheaths, waterproof housings, electrical shielding, and things like that. Regular calibration. Instrument drift is a major source of failure, so we should restore the accuracy, prevent unsafe measurements, improve reliability in this way. Self-calibrating intelligent sensors provide additional advantages. This is kind of nice. And these days, well, not even these days, it's been around for a long time, but we have even like self-winding watches. You know what those are? Self-winding watches are cool because they basically recalibrate themselves. You turn it on once. Yeah, you turn it on once and then just let it keep going. It could basically go forever. It's a self-calibrating watch, basically. It's self-winding. A long time ago, you used to have to wind those things yourself once they ran out of juice. But now we have self-winding watches. Great. This is redundancy. Redundancy means adding duplicate components in parallel. For example, right here, especially at weak links. Right here, duplicate components that have poor reliability. Yeah, so I mean, the more redundant you get, the better it is. I heard this one advice about redundancy with saving your files. There's a 3-2-1 system. The 3-2-1 system is like you need 3 backup copies over 2 mediums, and one of them should be off-site. So 3 backup copies means, on your computer you have 1 copy, in the cloud you have 1 copy, and maybe in a hard drive somewhere you have 1 copy. Those are 3. Over 2 different mediums, that would be like one would be the cloud medium and one would be, even you could have physical medium like DVDs or something like that. And one should be off-site. That means, like whatever you're storing, you can't keep it all in your house only, because what if your house catches on fire? You lose all of your information, So think about that for photo storage. Let's see if we can find this. One of my friends, a long time ago, he had photos on his Mac computer, and his Mac computer died. And so he lost all of his photos. He was a photographer. He lost all of his photos for years, So let's see this. Maintain at least 3 copies of your data. Keep 2 copies stored at separate locations, and then store at least 1 copy at an off-site location. This is a good way to deal with redundancy of your files. And this is why I do a lot of things through GitHub and Google Drive and things like that, because I save 1 copy on my hard drive on my computer, and then I save 1 copy in the cloud, and I should actually have another 3rd copy somewhere, but I haven't yet done that. But 2 different locations, one's in the cloud, one's on my device. So I feel pretty secure saving my documents, because even if my whole computer crashes, everything that's important to me, all the papers I'm working on, everything, I've already backed it up in Google Drive or in GitHub. So it makes it really secure, and I don't have many worries about losing my files, my important files. Let's see. Anyway, redundancy. Yeah. For example, if one instrument has a 95% reliability, if you add them in parallel, it has a 99.75% reliability rating. That's much better. Software differs from hardware fundamentally. Hardware fails because of age, wear, and environmental damage. What about software? It fails because hidden programming errors already exist. Certain inputs trigger those errors. Yeah, so sometimes your program just crashes. Software does not usually physically deteriorate over time. So the thing with crashes, uh, yeah, your software, the code itself, it won't deteriorate over time, but if there are coding errors, you could lose data. However, your hard drive is hardware. So your hard drive may age, it may wear, it may suffer environmental damage, and that could fail over time. So that's why, keep your software backed up. Keep your files backed up somewhere, especially in the cloud. I really recommend it. These days, OneDrive, Microsoft OneDrive is also good. It can keep your desktop computer like synchronized with the cloud, basically. So it's also a good strategy. I'm considering implementing that in the summer. Software reliability. When we talk about software errors, we can talk about detected errors, D, undetected errors, U, and total errors. So the equation for this is how many undetected errors are there? Well, how many total errors are there minus the number of detected errors, right? And then you could switch these around to see. The true value of T is unknown, so software can never be proven perfectly error-free. However, you can find a large number of errors, you can detect a large number of errors, and then there are some bugs where you're like, we didn't detect that one. How do we find that one? And this is what software engineers deal with a lot. How to find bugs that they can't find. That's why on GitHub, for example, let me show you GitHub, for example. I'll show you even this course's webpage. One of the nice things about GitHub for open source software and things like that. Hurry up and go. Oh, I put GitHub with 2 H's. That's why it's not going. And then I also spelled courses wrong. Okay, now it's going to go. Okay, yeah, so for example, this is all of the code for our current website. And over here in issues, this is a nice thing that people can do. When something breaks on the website, the developer, like me, I don't necessarily notice that something breaks because I'm not using the website the way my users are using the website. So what the users can do when there's an error is they can come over to GitHub and publish an issue. They can add a new issue and describe what's the error that they found. How did they produce the error? Like what were they doing on my website that made the website break? And in that way, I can reproduce the same error that they had if I follow the same steps that they followed to get the error in the first place. Then I can reproduce the error and I can fix the error. Otherwise, I just don't know what my users are experiencing. So that's a good way to take care of dealing with problems and issues and bugs on the website is let the users report the bugs to the developer. The developer recreates the bugs and then fixes the bugs. That's one of the best ways to fix this undetected errors problem. I can't detect all the errors, but my users detect way more errors. Tell me how to fix it, or tell me what the error was, and then I can reproduce it and fix it. That's a good way. Software reliability. Another thing we could talk about is error seeding. Error seeding estimates hidden software errors by intentionally adding known errors to a program. This is maybe slightly similar as what white hat hackers would do. Like you intentionally hack something in order to find out what the bugs and errors are. So detected real errors multiplied by the seeded errors. These are the errors that you purposefully put into this software. Divided by the detected seeded errors. So what errors you put in there, right? And then whatever you can detect, those are the ones you divide by. So then the detected real errors divided times the seeded errors divided by your detected seeded errors equals the total number of errors. And this is a long explanation talking all about error seeding. And if you are interested in that, go ahead and read that a little bit. I added it for your benefit. Okay. This is an example. The author of a digital signal processing algorithm that forms a software component within a measurement system adds 12 deliberate faults to the program. The program is tested by a second programmer who finds 34 errors. Of these detected errors, the program author recognizes 10 of them as his errors that he put into the program. So, in order to solve this, we take down here. The total number of errors is 34. 10 of those were seeded errors. The total number of seeded errors was 12. So the detected errors minus the seeded errors are 24. Then the total errors can be 24 times 12 divided by 10, which is 28.8 actual total errors that you can find, you can determine. Okay, another approach to software reliability is called the double testing approach, and this is very, very common in not only companies but also in research. Two independent testers examine the same software for errors. This is also what we call beta testing, game beta testing. I will give you a nice image of that. Because this was my dream job when I was a kid, Oh man, wouldn't it be great to be a beta tester? Your whole life, all you do is play video games and you just try to find what's the problems. You try to break their software, right? And then you report it. I'm gonna shut this down pretty soon. So, yeah. So the nice thing, or the thing about this job, being a beta tester, is you think that you're gonna have a really nice life just playing games all the time, but it's really difficult because you have to write reports, long reports, cataloging all of the failures, all of the things you detected, and it takes a long time to find some of those things. You have to play through the whole game. You have to, go to all the locations. You have to find all the things. So it's a long, arduous process. This is real work, and I'm sure that they don't pay you a lot of money because you want to play the game. But a lot of beta testers that I've seen with interviews and things like that, they say, oh, that was so tough. I don't ever want to be a beta tester again, kind of thing. Anyway, here's the formula for this. The total number of errors equals the detected errors from one tester multiplied by the detected errors of the second tester divided by the common errors found between both of them. Make sense? Over here again, this is the how they calculate that, how they come up to that formula. And you can read that yourself if you want. Here's an example. A piece of software is tested independently by two programmers, and the number of errors found is 24 and 26 respectively. Of the errors found by programmer 1, 21 are the same as those found by programmer 2. So D1 is 24, D2 is 26, and C is 22. Therefore, plugging those numbers in, we get 24 times 26 divided by 21, and the total errors that come out is 29.7 total errors. Yeah. Okay. Another version of software reliability, another method is N-version programming. And here is another software error. Talking about seed errors, something like that. Anyway, this is a little bit different from N-version programming, but I added it because I think it's useful also. You can read it yourself, though. Critical systems often use multiple independently written versions of the same software, usually 3 or 5 versions. This is also something called, well, we can do A/B testing, in YouTube video thumbnails and things like that. It's kind of a similar idea. Outputs are compared against voting logic. This reduces the probability of system failure. Let me show you a little bit of that. A/B testing in YouTube. A/B testing. Yeah, so you can do A/B testing in YouTube. This is kind of useful. For example, like this. You show thumbnail A to half of your audience, you show thumbnail B to half of your audience, and whichever thumbnail gets the most views, that's the one you end up using, something like that. So, it's a little bit similar, not quite the same, but it's a little bit similar. You create multiple versions of the same software, and then whichever version is the most error-free and the most reliable is the one you end up using. Here's an example. A program is tested and an estimate of 24 is obtained for the total number of errors. The program is seeded with, oh, this is the PW one, so this is a little bit different. Anyway, the program is seeded with 30 deliberate errors and further testing is carried out until all 30 seeded errors have been found. If no new previously undetected errors are found during this further testing to find the seeded errors, calculate the probability that the program is completely error-free. If no new errors are found during the second stage of testing, the probability that the program is error-free can be expressed by the expression P, where the given value W, this is the seeded errors, 30, and then P, the probability that it's error-free, equals W, the original number, divided by W plus 1. There might be one additional error that you didn't find yet, but the probability that it's error-free is 96.8%. That's pretty reliable. Okay. We can also use safety-oriented languages such as Ada, which contains features designed to reduce programming errors. Yeah, I don't have an example about that, but anyway, Ada is a language for software help. Ada language, software, Ada software language right there. Here's a programming language called Ada. This allows, this is used with Spark, and it's one of the most reliable programming languages available for development of high-integrity applications. That would be something that is very interesting to look at later. So I'm going to link it. Okay. Actually, I'm going to take a screenshot of that too, so that we can remember what it looks like. My daughter is here and supposed to go to Hagwon right now, Academy, and sounds like she was being slow. And that's why you might have heard some voices and doors. Okay, anyway. Unit 3 is about safety systems. Safety systems monitor industrial processes and respond when dangerous conditions occur. Some of these are alarms, automatic shutdowns, or emergency actuators. Let me show you a picture of this. For example, things like this, you can have cameras that detect people, and these people, if they're not working on the machine, this machine is supposed to be off, right? So this machine is supposed to be off when they're working on it. So in this case, if the machine is off, you would have a sensor that detects whether the machine is off or on. If the machine is off and there's people off of this green path, then it's deemed safe, But if this machine is on and there's people off of this green path, then it's deemed unsafe, and they would probably shut this down or send a warning message like, get on the path, beep, 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 something like that. So this is a really good thing that people are using in industry these days. Long time ago, there was a book in America called The Jungle Book, published in 1967. No, not that. The Jungle. Sinclair. Yeah, The Jungle Sinclair. This one. The Jungle by, what's his name? Sinclair? Upton Sinclair. It was fiction, but it looked at the dangers of working in industry, kind of like this. And it basically described certain situations, like an event where a guy, like, let's say it was a meat processing plant or something like that, and so they would let the cows be thrown into like a meat grinder or something like that. And this particular plant, it doesn't have safety rails around the meat grinding area. So a worker maybe was walking past one day and he fell in, and then he got ground up, And so this book was kind of eye-opening at that time, to let people be like, oh, wow, this is kind of dangerous. We should update our safety regulations in these meat processing plants and things. Yeah, anyway, that was kind of crazy. Safety legislation. Safety laws define responsibilities for both employers and employees. Employees must provide safe equipment, train their workers, and install safety systems. In Korea, that's why we have the 폭력 예방. Every year, I have to do the same thing every year. 폭력 Yebang. Gyoyuk. Every single year, every single school, I have to do this. This is like about discrimination and sexual discrimination and not, you know, yeah. Anyway, it's about discrimination, abuse, things like that. We have to do this every single year. This is one of the trainings that I have to continually update myself about that employers must do. I'm going to put that in green because that's the green one. Employers must. Let's make it a little bit lighter green. That's better. Employers must provide training like this, train workers. Employees must protect themselves. This one I think is important. Also protect others. Give your friend a warning if he's too close to something. Avoid damaging safety systems. One thing that I learned is biking. As I'm biking, just remember, everyone is trying to kill you when you're biking. I don't think these posters are great, but one thing that I was taught when I'm biking, especially in Korea, is just imagine that not everything, but everyone in Korea who's driving a car is trying to kill you. Yeah, everyone who's driving a car is trying to kill you. So always be alert, always protect yourself. Yeah, biking in Korea, danger. Let's check that. Yeah, like this. Just imagine that everyone around you is always trying to kill you in Korea. So protect yourself, especially in Korea. It's dangerous. Oh, there was this video I saw. Let me show you this video. Biking BMW. I don't know if you saw this one, BMW. This one I saw recently. Biking BMW news. It should be famous. Yeah, it's right here. This one.
It's nail-biting video of a BMW case of road rage. Here's Jim Murray.
It's car versus cyclists, and it's open.
This is stupid, right? He's in the bike lane. He's in the bike lane, but the BMW's like, get out of the way. And he's honking his horn.
War. Watch as the BMW honks and dangerously tails the cyclist who's riding in the designated bike lane. The cyclist, fearing he'll be hit, jumps his bike onto the sidewalk.
And then he comes up to the other one. There's a second biker.
BMW races towards another cyclist who's also in the bike lane. Someone in the BMW throws a water bottle and flips him off. Cyclist Luke Fetzer says the trouble started when the BMW driver first swerved at them at an intersection. We see somebody jump.
It's awesome, right? Yeah, I have experienced the same thing in Korea before. I've experienced people trying to kill me, cut me off. People have hit me. Buses have hit me. You just have to be always way more alert than the drivers. The drivers here, they are trying to kill you, actively trying to kill you. So, I mean, this is a bit of an exaggeration, but you got to be careful. You got to protect yourself in Korea, without a doubt. I've been hit like 11 or 12 times in Korea. I have a scar from some of them that I've been hit, like no joke, no joke, especially on right turns. Ugh. It used to be cars had the right of way in Korea, like cars first, people, you just get killed. It's not supposed to be a joke, but that's true. And then a few years ago, they instigated a new law in Korea which said if the walk symbol is on for the walkers, then cars have to stop first. And so finally people started doing that. I was here though when the walk symbol would be on and the cars would just go, 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 go. And even though there's people trying to cross the street walking, the cars don't let them. The cars just go, 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 go and honk at the people, even though the people have a walk sign. I was here for that. That was nuts. Okay. Intrinsic safety. Intrinsic safety means systems can operate safely in explosive environments without causing sparks or fires. These are common in chemical plants, oil refineries, and gas facilities. And that one, the aluminum factory, needed it. Let's copy paste that aluminum factory one more time. The aluminum factory really, really needed that. Yeah, too bad you didn't have intrinsic safety here. Okay, installation practice. Proper installation prevents electric shock, dangerous cable contact, signal interference. Signal cables and main cables are normally kept separate. Yeah, please keep those separate. Here is the standard for this. IEC 61508 defines best practices for safety systems. I did link that previously, I believe. The standard addresses safety management, personnel competence, and technical safety requirements. Next is safety integrity level. This is called SIL. I have a friend whose name was SIL before. SIL measures confidence that a safety system will function correctly during dangerous conditions. The higher the SIL value, the lower the failure probability, the greater the reliability. There's 4 levels in SIL. It's determined through risk analysis. So in SIL level 1, the probability of dangerous failure per hour is still pretty low, 10 to the minus 6th. But the probability of dangerous failure per year is 10 to the minus 1, which is pretty high, actually. Safety level 4 is 10 to the minus 9th, down to 10 to the minus 5th. Not bad. Designing safety systems. Here's a diagram. We monitor a process in the sensor. We should have a trip amplifier, an actuator or an alarm, and then a response to failure. So this is how physical AI works. Physical AI basically senses something. It uses sensors to sense something. It processes things. It amplifies or processes things, and then an actuator takes some action. So from sensing to processing to actuating to action. Sense, process, action. Like that. That's physical AI in a nutshell. Basic safety systems contain sensors, amplifiers, or some kind of processing, and then alarms. Examples would be pressure sensors. You step on, this is like Indiana Jones, for crying out loud. You step on something, and then it triggers something. Let's see. Sensor, Indiana Jones, boulder. Did you ever see that? Yeah, he like steps on something wrong. He steps on a sensor, a pressure sensor, and then the boulder starts rolling at him. Run away. Be careful of that. Pressure sensors. Signal amplifiers or relief valves are all part of that. Microprocessor-based protection systems include embedded processors, intelligent software, trend analysis. Software reliability is really important in these systems. We also have 2 out of 3 voting systems where 3 independent safety systems operate simultaneously. Shutdown occurs if any 2 systems agree that danger exists, and here's a formula to calculate that. This provides very high reliability. We monitor these 3 systems, and if any 2 of those vote that it's dangerous, then we have to respond. But if, 2 of them are like, it's okay, and one of them says, it's not okay, then you ignore the one, because it's 2 out of 3 voting. Standby systems. Here's a diagram of a standby system. We monitor some kind of process variable. We check what's happening. We detect if there's a system failure, and then we can switch to respond to the failure. Standby systems use one active system and one backup system. The backup activates only if the main system fails. This is like a backup generator, eMart, over here next to me, eMart famously went out of business a few months ago because the guy didn't pay his electric bills. So the night that happened, I remember I drove past it, and like all the lights were off except for these very dim, backup lights to make sure that people could escape properly once Ginger City shut the power off. Advantages of this are its lower cost. Disadvantages is it requires reliable switching over here to the backup, and it requires reliable fault detection. This is also something that would happen in Jurassic Park, for example. You remember Jurassic Park? Like the dinosaur escapes, the whole system shuts down. Well, then you need the backup system to come on, so at least you can have lights to light your way out of the park. Here's an example. In a particular protection system, 3 safety systems are connected in parallel, and a 2 out of 3 voting strategy is applied. If the reliability of the 3 systems is 0.95, that's calculated here, 0.95 times to the 3rd power, calculate the overall reliability of the whole protection system. So that would be 0.95 cubed plus 3 times 0.95 squared times 1 minus 0.95. The whole system is 0.993% reliable. Let's skip this one for now. It's kind of similar. Okay, actuators and alarms. Safety systems end with automatic actuators or human-operated alarms. Alarm design is extremely important because too many alarms cause alarm fatigue, right? It's like the boy who cried wolf. I don't know if you ever heard that story. The boy who cried wolf. You probably have similar stories in your culture, but this is what happened. The boy who cried wolf. The boy who cried wolf basically says there was a boy who was out guarding his sheep and he was bored. So because he was bored, he was like, what if I said a wolf came? So he yelled, wolf, wolf, wolf. And all the villagers came and they're like, we're going to defend the sheep and we're going to help. And then there was no wolf. And he kind of giggled, that was fun. And then they went back, there's no wolf. Did the wolf run away? And then the boy, few days later or something, he did the same thing. He cried wolf again. The villagers came again to help. And then, no wolf again. And then third, fourth time it happened, they kept coming. Finally, the fifth or sixth time, they're so tired of it. They're like, he's just joking with us. Well, then a wolf really did come, and the boy cried, no, for real this time, guys. There's really a wolf this time, guys. He cried wolf, and there was a real wolf, and the villagers were like, hey, he's just lying, so they didn't come. So if you have too many alarms, you'll have alarm fatigue and you'll start ignoring your alarms. That's the same thing that happens when you have your alarm go off in the morning and you're like, snooze, snooze, snooze. Eventually you don't hear the alarm anymore. So wake up with the first alarm. Operators may begin ignoring alarms. That's what I'm saying. Danger alarms, therefore, should be rare, prominent, and difficult to ignore. That's what this fire alarm system in this building is. It's difficult to ignore, and it's almost never. And it is so loud. Wow. When it's happening. Okay, here's a summary of the chapter. That was good because that took about the class time. This chapter introduced measurement system reliability, reliability calculations, hardware reliability, software reliability, safety systems, industrial safety standards. This chapter emphasizes that reliable measurement systems are essential not only for accurate measurements, but also for protecting equipment, industrial processes, and your life. Key ideas include the mean time between failures, the mean time to failure, the mean time to repair, and availability. Those were all the first concepts. Series and parallel reliability laws, redundancy, calibration, recalibration, and protection, error seeding and software testing, end version programming, IEC 61508, and safety, what was that? I don't even remember. Safety integrity level, voting-based safety systems, and alarm system design. Great. That is the end of this slide. In the next slide, we will take a look at your kit, your Internet of Things kit. We're going to install the Mosquito server. We're going to put all of the files onto your kit, and we are going to play around with the kit a little bit, and it's going to be fun. So I might even add some other window over here where I can make myself full screen to show you what the kit is doing, hold the kit up like this and show you what the kit is doing. So that should be fun. Okay, we'll see you in the next video. Bye now.